Section 9 of the Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Edward Labonte. The Science History of the Universe, Volume 1, edited by Francis Rolt-Wheeler, Astronomy, Chapter 8, The Solar System, Modern Investigation, Part 1. The Ptolemaic system of astronomy was discredited only at an epoch nearly simultaneous with that of the discovery of the New World by Columbus. The true arrangement of the solar system was then expounded by Nicholas Copernicus, 1473 to 1543, in the great work De Revolutionibus, to which he devoted his life. The first principle established by these labors showed the diurnal movement of the heavens to be due to the rotation of the Earth on its axis. Copernicus pointed out the fundamental difference between real motions and apparent motions. He proved that the appearances presented in the daily rising and setting of the sun and the stars could be accounted for by the supposition that the Earth rotated just as satisfactorily as by the more cumbrous supposition of Hipparchus and Ptolemy. He showed, moreover, that if the ancient supposition were true, the stars must have an almost infinite velocity, and declared that the rotation of the entire universe around the Earth was clearly preposterous. The second great principle, which has conferred immortal glory on Copernicus, assigned to the Earth its true position in the universe. Copernicus transferred the center about which all the planets revolve from the Earth to the Sun, and he established the somewhat crushing truth that the Earth is merely a planet pursuing a track between the paths of Venus and of Mars, and subordinated, like all the other planets, to the supreme sway of the Sun. This great revolution swept from astronomy those distorted views of the Earth's importance which arose, perhaps not unnaturally, from the fact that the observers chanced to live on this particular planet. Whether the actual services rendered by Copernicus are commensurate with his fame may be doubted. He labored under the weight of an ecclesiastical tradition that could not be abandoned without some risk. He was a bold man indeed, who dared to overthrow or even to question orthodoxy and to diminish the Earth's overshadowing importance in the solar system. The Copernican system was not flawless either in theory or logic, and many objections could be made to it, particularly by an astronomer who had observed and studied the movements of the heavenly bodies. After the example of the ancients, Copernicus assumed as an axiom the uniform circular motion of the planets, and as the only motions which are observed are in a state of incessant variation, he was obliged, in order to explain the inequalities, to suppose a different center for each of the orbits. The Sun was placed within the orbit of each of the planets, but not in the center of any of them. In other words, he still adhered to a system of epicycles. Consequently, the Sun performed no other office than to distribute light and heat. Excluded from any influence on the system, the Sun became a stranger to all the motions. The fixed stars were alleged to be stationary, and it was necessary to suppose that they were almost infinitely distant, inasmuch as they always seemed to preserve the same position when viewed from the opposite sides of the Earth's orbit. While various astronomers showed some disposition to accept the Copernican teaching, most of them were bitterly opposed to it on ecclesiastical, traditionary, and scientific grounds. Tycho Brahe, 1546 to 1601, was the most distinguished of these opponents. Being an indefatigable observer and practically the first to realize the value of continuous observation, he enriched astronomy by a star catalogue and studies of the movements of the other heavenly bodies. Tycho accepted the Copernican conception of a central sun, but rejected the idea that the Earth moved. Thus he sought to effect a compromise between the Ptolemaic and Copernican systems. It was the study of a comet in 1577 that led Tycho to formulate his ideas of the solar system. He believed that the comet X as shown in the accompanying diagram, was revolving around the Sun at a distance greater than that of Venus, and assumed that both the Sun C and the Earth A were centers of revolving systems, the 5 planets revolving around the Sun and the entire system in turn moving around the Earth. This incorrect proposition, which was one of the least of Tycho Brahe's contributions to astronomical science, is significant, showing as it does how difficult it was for the principles of Copernicus firmly to establish themselves and planetary motion to be explained satisfactorily. Whatever Tycho may have thought of the Copernican system, his contemporary Galileo (1564 to 1642) was willing to accept it. It has been shown how Galileo, with the telescope of his invention, was able to extend astronomical science and to introduce new methods of observation which came naturally to one who was a leader in the experimental science of his time. But even before his work with the telescope, Galileo had adopted the astronomical views of Copernicus and collected arguments for their support. He was able in 1604 to confirm the discovery of Tycho Brahe that changes take place in the heavens beyond the planets, and that there was an important region beyond the Earth and its immediate surroundings. As was but natural, the use of the telescope broadened Galileo's horizon, and true scientist that he was, he immediately brought to bear his new discoveries on the fundamental conceptions. Thus his discovery of the satellites revolving around Jupiter as the planets themselves revolved around the Sun not only rendered necessary the explanation of these new bodies, but dealt a serious blow to the infallibility of Aristotle and Ptolemy, neither of whom had any idea of the existence of these satellites. Further support was given to the Copernican theory by the ocular demonstration of these satellites revolving around Jupiter and not dropping behind, just as the Moon was required to move around the Earth, a mechanical difficulty brought forward by the opponents of the Copernican idea. As Galileo developed his astronomical ideas and discoveries, he naturally came into conflict with ecclesiastical authority, and there began the unfortunate controversy as to the relative validity in scientific matters of observation and reasoning on the one hand, and the authority of the Church and Bible on the other. Controversies such as this were conspicuous in the latter part of Galileo's life. They culminated in his famous trial and formal abjuration of his alleged errors, and in his conviction, quote, of believing and holding the doctrines false and contrary to the holy and divine scriptures, that the Sun is the center of the world, and that it does not move from east to west, and that the Earth does move and is not the center of the world. Also that an opinion can be held and supported as probable after it has been declared and decreed contrary to Holy Scriptures, unquote. Despite Galileo's abjuration, his general attitude toward the Church and Bible is contained in his approval of the saying of Cardinal Baronius, quote, that the intention of the Holy Ghost is to teach us not how the heavens go, but how to go to heaven, unquote. His attempts to explain and demonstrate the Copernican system in his great astronomical treatise, Dialogue on the Two Chief Systems of the World, the Ptolemaic and Copernican, led to his trial and conviction before the Inquisition. Kepler, another of Galileo's contemporaries, did more even than the great Italian to bring about a proper conception of the solar system and the motions of the planets. A student under Tycho, it was but natural that Kepler should have imbibed from his master a respect for systematic observation, regardless of the correctness or incorrectness of Copernican views. As a result, Kepler early adopted the Copernican doctrine, opposed though it was by his master. His observations led him to the conclusion, however, that even Copernicus had not revealed all the mysteries of planetary motion, and that the hypothetical circles in which the planets revolved around the Sun, according to Copernicus, did not agree with the paths observed. Under the instruction of Tycho, Kepler addressed himself to the problems involved in the planet Mars, whose positions as seen in the sky were a combined result of its own motion and that of the Earth, as both move around the Sun. Actual observation of the planet and the consideration of various geometrical theories that suggested themselves eventually led to the conception that the path of the planet must be some form of an oval. Finally, Kepler reached the conclusion that instead of being circular, the planet's motion must lie in the simple curve known as an ellipse, and formed by taking an oblique section of a cone. While the circle has but a single center, the ellipse depends for its form upon two fixed points, each of which is termed a focus. It can be drawn by using two pins stuck in a sheet of paper and by inserting a pencil within a loop of string that also includes the two pins. The curve may be traced by moving the pencil while the string is kept taut. It will be found that if the 2 points are kept close together, the curve approaches in form a circle, while if they are separated, the figure becomes elongated and possesses what the mathematicians term greater eccentricity. At any rate, every point on the curve is such that the sum of its distance from the two foci is always the same. Kepler found that the Sun was at one focus. When the planet was near that focus, it moved with greater velocity than when at the opposite part of its orbit. The speed of motion, however, was always proportional to the area swept out by a straight line from the Sun in equal intervals of time. In other words, there were formulated the now famous first and second laws of Kepler as follows. 1. The planet describes an ellipse, the Sun being in one focus. 2. The straight line joining the planet to the Sun sweeps out equal areas in any two equal intervals of time. Kepler not only established these laws for Mars, but immediately applied his principle to Earth, and then claimed, without proof however, in his Epitome of the Copernican Astronomy, that these two fundamental laws applied also to all the planets and to the motions of the Moon. Accompanying these two laws was the third already discussed, in which it is stated that the squares of the times of revolution of any two planets, including the Earth, about the Sun are proportional to the cubes of their mean distances from the Sun. It was the disclosure of these wonderfully simple relations that laid the foundation for the Newtonian law of gravitation. Contemporary judgment, of course, could not anticipate the culmination of a later generation. What it could understand was that the first law of Kepler attacked one of the most time-honored of metaphysical conceptions, the Aristotelian idea that the circle is the perfect figure and that planetary motions, consequently, must be circular. Not even Copernicus had doubted the validity of this assumption. Kepler was too great a genius to rest content with the mere observation that the planets move in ellipses. Next, he desired to determine why they do so move. It remained for Isaac Newton, 1643 to 1727, to answer the question satisfactorily. Yet Kepler had a curious premonition of the law of gravitation. Quote, "Whereas the Ptolemaic system," unquote, comments Berry, quote, "required a number of motions round mere geometrical points, centers of epicycles or eccentrics, equants, etc., unoccupied by any real body, and many such motions were still required by Copernicus, Kepler's scheme of the solar system placed a real body, the Sun, at the most important point connected with the path of each planet, and dealt similarly with the Moon's motion round the Earth, and with that of the 4 satellites round Jupiter. Motions of revolution came, in fact, to be associated not with some central point, but with some central body, and it became therefore an inquiry of interest to ascertain if there were any connection between the motion and the central body. The property possessed by a magnet of attracting a piece of iron at some little distance from it suggested a possible analogy to Kepler, who had read with care and was evidently impressed by the treatise On the Magnet, De Magnete, published in 1600 by William Gilbert of Colchester, 1540 to 1603. He suggested that the planets might thus be regarded as sharing to some extent the Sun's own motion of revolution. In other words, a certain carrying virtue spread out from the Sun, with or like the rays of light and heat, and tried to carry the planets around the Sun. Kepler says himself in his Epitome, quote, There is therefore a conflict between the carrying power of the Sun and the impotence or material sluggishness (inertia) of the planet. Each enjoys some measure of victory, for the former moves the planet from its position and the latter frees the planet's body to some extent from the bonds in which it is thus held, but only to be captured again by another portion of this rotary virtue." Unquote. Thus is faintly indicated the great theory of gravitation which, as developed by Newton, was to supply a satisfactory explanation of planetary motion, and which is the underlying basis of all modern astronomy. Newton had become convinced that the attracting power of the Earth extended even to the Moon, and that the acceleration produced in any body, whether it be as distant as the Moon or close to the Earth, was inversely proportional to the square of the distance from the Earth's center, and also proportional to the mass of the body. Then he found that the motions of the planets could be explained by an attraction toward the Sun, which produced an acceleration inversely proportional to the square of the distance from the center of the Sun, not only in the same planet, in different parts of its path, but also in different planets. Again, it follows from this that the Sun attracts any planet with a force inversely proportional to the square of the distance of the planet from the Sun's center, and also proportional to the mass of the planet. Accordingly, if the Earth or Sun attracts a body, the body must exert a similar force on the Earth or the Sun, and gravitation is not only a property of the central body of a revolving system, but belongs to every planet in just the same way as to the Sun and to a moon, or to a stone, just as to the Earth. After Newton had established provisionally the law of gravitation and the laws of motion, it remained for him to prove that the observed motions of the planets agreed with those calculated. A situation of the greatest complexity, however, was relieved by the fact that the mass of even the largest planets is so very much less than that of the Sun that the motion of any single planet is affected but slightly by the others, and it may be assumed to be moving very nearly as it would if the other planets did not exist, due allowance being made subsequently for minor disturbances or perturbations produced in its path. One by one the various irregularities observed were explained, and the motion of the Moon and its various eccentricities were computed with accurate numerical results. End of section 9.